So I guess I want to say first, there's a rule. What's that?
A regular language is one that you can write a regular expression for. Right?
Yeah.
In an arbitrary language, there's no pattern, so you can't pick it up.
An arbitrary, that's the rule of thumb is basically, so, So all languages say, remember, all possible languages, this is not, so this cannot be methodically listed. You know, in a sequence. But we said, say, like, the, what were they called again? The regular languages. So the question is, what's the intuition? What's the rule of thumb? The rule of thumb is, you know, so the idea is that if each language, I guess if it can be specified by a finite amount of stuff, if there's a finite amount of information that will give you the specs for the language, any class like that so can be enumerated. So the class of regular languages, each regular language is specified by a finite state machine. It's a finite amount of stuff. So there's a methodical way to list all of those things. The problem here is there's infinitely many things. There's infinitely many. The data you need to specify an arbitrary language is an infinite number of coin flips. So you can't. There's no way to methodically list all those. All right. So the idea is, so if each language is specified by a finite amount of information, so we can list them. So, for example, how would I list all the possible machines? So, I'll just start. But for example, so remember we had this table, right? So you could have, say the alphabet 0 and 1. You have say A and B. You have state 1. So like, what's the smallest machine? Is one with one state, right? The start has to be 1. And there's two choices either. The final state can be nothing, or the start can be 1 and the final state could be 1. Right? Those are the two choices. And I have to go back to 1. So I could turn this into a string, right? I could code it up into a string. So this could be something like, 1 1A1 1B1 the start state and my list of final states. So this would be this is the first string in a scheme-like notation, right? So here's my list of I guess this is the probably need a few more parentheses, but the idea is here's yeah. So here's state and its transitions. Here's the start states. And here's the final states.
I don't get this at all. I don't understand.
What am I doing?
Yeah.
This is just like a scheme notation. I have a list of stuff.
You said you have one state, though.
Yeah, the state is.
So if I would draw one circle, that would be the machine with some arrows.
This is the machine.
Okay.
So I'm just saying, I'm just picking a method to encode it.
Okay.
I mean, I don't have to pick. I picked scheme, list. So I have a list of a state with all of its transitions, and then so this is the state is 1. It has the transition on A go to 1, on B go to 1. The initial state. So after all the lists of all the states and the transitions, I can put the initial state and then the list of final states. There's no final states here, right? So my point is, so there's the first thing on the list. Just like before, I had a methodical list that went E, A. The list of all words was E, A, B, A, B, 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 et cetera, right? Here's my methodical list. This is just the first thing on the list. It gets tedious, right? But I can do the next thing on the list by putting a 1 in here. I can code everything into a string. So I can methodically list all finite state machines like this. start with all the machines with one state, go through all of them, go through all the machines with two states, and all the possible permutations, et cetera, et cetera. So all the finite state machines are listable. And so once I come up with this big list, so eventually, so this is like M1. If I do a lot of work, I can get a list M1, M2, M3, M4, dot, dot, dot. And I can do computations on that list now. So these could be my atoms, and I can say, well, which of these satisfies a certain property. But I just wanted to mention that's not really that important, but it is. It is and it isn't for you guys. So actually, I also wanted to mention, I'm being vague about what methodically listed is. You could question me there. What does that mean? Well, there's two possible definitions. Methodically listed. So one is called countable. That just means there is a list. If a set is countable, you can put it in. Well, there is a list for it. And then there's something called enumerable. I don't know, which is slightly different. Any idea what enumerable might mean? No, there is a computer program that will generate the list. This could be a list from God, or from, So we distinguish the idea that there is a list of things, that might. So it's a weird abstract idea. I mean, that there can exist lists that we can't generate with computer programs. So we don't. So we make that subtle distinction. More, like everything we're really interested in is. Well, yeah?
Could you just tie that into countably and uncountably infinite?
These are both countably infinite.
So there's a countably infinite that's not enumerable.
Yes, and that's what we're going to be talking about a lot. But basically there are things that are countably infinite that are, that someone like God or nobody, or depending on what your beliefs are, can put into a list. So there are things that are not listable via computer program. So the enumerable means there's a computer program. There's an algorithm.
What is the difference if they're both infinite? What is it that makes one listable and one not listable?
Well, they're both listable. It's just that this is a little more precise. You can just say, well, I mean.
Well, when we say there's an algorithm that can list it, we're kind of fudging it because it's not truly listing it if it's infinite.
No, but there's an algorithm that can list any arbitrary amount of it. If you want the first million of them, this algorithm will do that. Any finite portion of it. There can be things. There are a lot of collections we're talking about that are listable because they're subsets of. I mean, you could take subsets of things here. There are things that are definitely countable. They're subsets of, the natural numbers or subsets of the the language of all strings. So they're not bigger than the language of all strings. There is a way to list them, but not necessarily by computer program. So I mean, it's a really strange idea that we can accept that some things can be listed, but when you really get down to it, try and nail it down. What do you mean by list? If you say, well, there's an algorithm that can churn out that list, then suddenly there are distinctions. There are things that are not enumerable, even though you think they might be. So there's a slight distinction there. So in particular, every subset of every language can be methodic, is countable. Do you see why?
Every language?
Yeah.
Within itself is
Every stream of bits itself is countable. Not the collection of all streams of bits, but every stream of bits is countable. Do you guys buy that? Whoops. Why? No?
And countable has no connection to being able to actually get your arms around it.
No, countable doesn't mean you can generate it in any. So like, well, not an opera, but basically, well, maybe I'll leave it there for now. I don't know. Like, I think these ideas are best introduced slowly. I mean, for example, if you just flip a coin infinitely many times to decide which of these strings is in the set, that set is a list, right? If I just pick a random, this is a big list of all the words, and if I flip a coin infinitely many times, I can get a sublist of that by just, doing an infinite amount of work, flipping a coin for each one of these strings to decide whether it's in there or not. So that's listable, right? I mean, if you could do infinitely many things at once, you could list that thing, right? Because you just, for every word, you start with the first one, flip a coin. If it's one, put it in the list. If it's not, don't put it in the list. So you could do that infinitely often. And that's a stream of bits, that exists. It's countable, but there might not be any algorithm for generating it. Because flipping a coin infinitely often is not an algorithm that's reproducible. Right? So that's sort of the distinction. I mean, there's certain things so it is, you can generate a random stream of bits, but that's not, and that will produce some sort of list, but that's not an algorithm. And that's not something you could reproduce. So there's that kind of distinction. And that's really important. There's other non-random ways to specify things here. A lot of the interesting languages we're going to talk about, we can specify in some way, but it turns out there's no algorithm to generate them. All right. Anyway, I love this stuff. But it's very strange at first, the idea that something can exist without having some sort of way to generate it. All right, so what next? Do you guys want to do some push-down automata? What do you guys want to do? Do you want to go home? Do you guys want to work on those?
What's with this? Did we ever talk about this in class, this weird grammar thing?
Ambiguity in grammars? That's just a grammar.
It's just a grammar, it's just
Yeah.
different symbols.
Yeah, there's a typo though. I don't know if you got my email. There's a typo in it, so you should
Yeah.
print it out again. All right.
The only substantive change that the game class
Yeah. Yeah. Well, there's an it then else, which is really if then else.
That helps.
Yeah. Yeah. All right. So
You could say something about ambiguity.
ambiguity. I don't know if I have anything. If I can just generate one on the spot. Shy? It's a good shy question. We have a good.
Anything about ambiguity?
Yeah. Can we generate a? Yeah.
It begins with the letter A.
No. Do you have any ambiguous grammars off the top of your head?
Most grammars, if you just make them up, end up being ambiguous.
So I should just make one up?
Make one up.
I don't know. With my luck.
S goes to AA.
That's pretty good. Yeah, that's a good one. Or 1. Yeah. I guess that.
What's A go to?
Oh.
Zero. Put it to zero. Zero.
Yeah, why not? All right, so there's your assignment. Show that this is ambiguous.
Okay.
Show using what method? What would show? A parse tree would
I'm
show.
not sure it is.
Yeah. You also want A to go to epsilon. If A goes to 0 or epsilon,
It doesn't have to.
Doesn't have to.
is it ambiguous?
So ambiguous means that there's two different sort of derivations for the same string. So like he hit the man with the bat. There's two ways to parse it. Uh,
At least.
And then
yeah.
there's no other,
So
because AA can't get back in.
yeah.
I don't think that is ambiguous.
I don't think it's ambiguous.
I don't think it is.
You don't think it is? Oh, our luck.
What about,
How would you analyze it the front end?
couldn't,
Do you have to do it by
what about like
front?
001? Couldn't that be S goes to AA? Wait, no, it has to be.
Just make A go to 1 also, then it's.
All right, let's see.
Yeah, now it's definitely ambiguous. 1, 1 is ambiguous. It's kind of the same, ambiguous.
All right. So why is 1, 1 ambiguous?
So you can get it with AA or AS.
Right. Huh?
1 isn't ambiguous. The grammar is ambiguous because
Yeah.
1 has 2 parts. It's
Well
my
said.
job as the senior statement to be the pain in the ass with the terminology.
Yeah, you're absolutely
I
right.
used to be the scoffer with the terminology. Now I'm too old, so I can't believe it.
So what about 1, 1? So 1, 1, you could start with S, AA, say 1A, 1, 1. And what's the parse tree? One, what do you get here? Oh, you just get a 1, right? All right, what's the other parse tree?
S.
S. Oh, this is... So it seems really trivial when you give a trivial example, huh?
Well, the question is there a way to determine whether grammar is ambiguous without generating parse trees and tracking it down?
You just have to do it by drawing
Or is it just
Well, one thing, generally when you do splits, I mean, one rule of thumb...
Side of them.
Yeah, ambiguities.
You can't do it at all in any formal, organized way.
Yeah.
There's an infinite number
Yeah.
of different qualitative reasons of why a grammar is ambiguous. That's a good way to think of it.
Yeah.
You
Okay.
can't write down a finite set of criterion that will help you figure out whether a grammar is ambiguous or not. The best you can do is brute force, go through all the strings, and if it's not ambiguous, you'll find out it's not. Sorry, if it is ambiguous, you find out it will because you've got a mismatch. But otherwise, you'll never find out whether it's really unambiguous.
There must be certain key points.
Well,
so you can just-
splitting things up is one way, one thing that pops up a lot. If you have, if you have a break into, a lot of times if you have a break into AA, you might be able to do that in 2 different ways. Like you might, depending on how you subdivide A, there might be some ambiguity.
Right.
I mean, just chasing down the splits, I mean, that's generally where things can get ambiguous, because there's some choice, there might be some choice where you cut the thing into 2.
And
Here.
all LRK
Like-
grammars or deterministic context-free languages are unambiguous. That's an important theorem. And that's one of the reasons we create those.
All right. So, all right, that was pretty lame, ambiguous grammar, but it's ambiguous.
So to do that, like programming language, it's ambiguous. We just have to they have a hunch and take a shot at it.
Yeah, you got to use your intuition. That's one of the key results of this type of, like reasoning, is that somehow we'll never get rid of intuition. Somehow sometimes you need intuition to figure things out. You can't use a computer program to do it. You can't algorithmically do something. So it's it can be a very positive argument for the human mind that we just observe things and figure out things and guess well.
That's a good optimist point of view.
Yes. Yeah. The pessimist is like, it's hopeless. We might as well give
One
up.
more thing we can't decide.
Yeah.
Me.
I think it's a very positive thing for humanity in the mind. Yes. All right. So what's that? Yeah, our model for computers is wrong. Yeah, exactly. All right. So I guess we could work on 7 and 8. More practice on building these push-down automata. Actually, before we do that, I take that back. How about, you guys know how to convert, say, a grammar into a PDA? All right, it's a piece of cake, actually. It's a piece of cake. So let's yeah, no, they saw it. Seeing something is not knowing, right?
Okay.
That's all. All right, so let's just do a simple one. So it turns out it's actually a really simple thing to do. All right, we'll start with something unambiguous. And so here's the general idea for here's the PDA. Here's what it's going to look like. It's going to have, I guess, I don't know if I really even need the start state. I'll just. So here's the two loops. Expand the rules. And eat up the string.
You need to start.
Yeah, I guess I need the start, right? Why do I need the start? I'm not convinced.
Because if you just have it as a loop, then you have EZ, and are you saying it's non-deterministic anyway? So
Yeah.
I don't know. It's clear to write this way. Maybe you don't need it.
I'm not sure, but oh, here's a good reason. What we can do is we can push the start symbol onto the stack. That's a good thing to do.
Right.
As the first thing. Yeah.
You
That's,
could have that as part of the loop.
well, then you could push more start symbols onto the stack. That might be bad.
That might.
Yeah, I think that's bad. That's bad. Yeah.
Oh yeah, that gives you the star. That gives you the clean star.
Yeah.
Yeah, you need the star.
So basically, all you need is a bunch of. So it's actually a very simple concept.
Say it only has 3 states, so this is talking about something the same.
No, it's a very simple concept. All you need is, this is the general machine that turns a grammar into a PDA, is this machine. You just need some rules to expand the start symbols. The stack is where the derivation is going to be. And you just need some rules to eat up, bits of the string. And if you do all your expanding and, intersperse that with eating up the left-hand parts of the string, and you get all the expanding done and all the, canceling out the bits of the string, you'll get to an empty stack, and then you accept it. So what rules? So I want you guys to figure out what the expansion rules are there and the eating up the string rules are.
In this case, if we see S is the top thing on the stack, then push AB on the stack.
So I like this expansion rules, I guess. I like this sort of labeling the transitions and then putting, kind of like beta sim. You have a little thing, you click on it, and all the rules are on the side, instead of putting them on the transitions themselves. So what's the rule here? So no matter, I don't do anything to the input. And if I see an S on the stack, what do I put on the stack instead? AB. That's pretty much the only well.
Or BA.
Oh, you're right, BA. BA is, wait a sec.
Depends on how that.
No, I like AB. Because
Am I pushing on the stack first?
B. You're pushing B first on the stack. This is the top of the stack. What other expansion rules would I have?
That's it.
Well, I guess
If you see a 0,
if you see an A,
you put in
Put a 0 on there. No, that's not an eat up rule. No, we have to match this with a string, though.
Right, so if I see a zero, if I see a zero and there's an A on the stack, I pop.
If you read a 0, you pop the A. You don't put it on the stack.
This way will work in general. This is the way that it's done in the book, and there's a reason. There's a reason.
All right.
All right. Well, we can. I'm pretty sure there's a reason you have to do it this way.
Nothing ever gets popped. Where's the pop?
That's.
I don't see why you
I'm pretty sure you have to do this. I'm pretty sure because you have to. Well, I guess you could get away with it. I guess you could do it both ways.
No, you don't need to.
But I think this is nicer because you just sort of you have a derivation here, and then you have the eating up this string part, and you mix them. They're conceptually two different things. So you could make it one. But in any case, so what would the eating up the string rules be? So there's the expansion rules.
Well, once you pop the A, the B will be on top, and then you can change it, and then you can pop it.
Yeah, I don't know. I guess for me, you don't have. Let me give you an example. You don't have to do it this way, but there's two distinct things that are going on here. One is you're expanding, and at some point you have to eat up stuff as well. You have to do them, both of these things, and you have to kind of mix them. So I don't know. I like to keep them separate.
The thing is that a leftmost derivation in Science normal form has all the things you've already read to the left of you,
Right.
and all the things you haven't yet expanded to the right.
Right, but you don't need to put something in Chomsky normal form to do this rule. This works for any grammar.
This might work.
Yeah, this works for any grammar.
Including non-terminals that turn into many.
Yeah.
Right.
Yeah, maybe that. Sorry.
So, for example, let's run this machine. Let's do 1, 0, 1 through this machine. What happens? What's the first thing that happens? So I have a stack. So the first thing I do is put S on there. I don't know a good notation for this. So there's my state there. And then S goes to AB. Then what happens? A goes to 0. Then what happens? Now I can't do an expansion rule, right? Because the 0 is blocking me. All right, so I have to do an eat up the string rule. Right, so this becomes, yeah, you read that 1 off, and that allows you to pop. And now I can't do a reading rule because I don't have any symbols to pop. So I have to do an expansion rule.
Can you say that again? You can't do a reading rule because you don't have any symbols to pop?
Well, I don't have any characters, any terminal symbols at the top of the stack. The only reading rules are if you have a terminal there, pop it off. That matches your string.
So what is at the top of this stack?
The top of the stack right now
Yeah.
is there's a B.
Okay. Okay.
So when you made the A go to 0, you replaced the A with a 0.
Yeah,
So you pop the A and you just push to 0.
yeah. So I'll give you a more complicated one too, like equal numbers of zeros and ones. But let's finish this one. What would be next?
Change the B to a 1.
Right. So you change the B to a 1. And now I can't expand, but I can munch up strings. Gobble, gobble. All right, and then accept, because I have no more string. So what if I had, say, like 0 to the n, 1 to the n? 0 S1 or epsilon. So what would the rules be? So the expansion rules are what? It's the same machine. You just change the little programming block, like in Betasim or something. Yeah, Rizzo?
So, I don't understand. That's what you would write down as the PDA generated? Or the
Yeah, this PDA accepts that grammar. So it's the same structure. You just change the rules. You just put in this is where you put the grammar rules, and this is just trivial. Yeah. So basically all you're doing is rewriting the grammar right there. And that machine will always accept exactly the same language.
And it's a deterministic.
No, it's not deterministic because you could, or is it
Lots
deterministic?
of different ways to expand. Say there was a 0 on, I'm sorry, A on the stack that goes to a bunch of different things. And you wanna-
Yeah, there's a lot of different rules. That's exactly why. I could take, just like if something's ambiguous, there could be many derivations. In this case, it is deterministic. This is a deterministic machine. But yeah?
Where in there are we deciding, where's it telling us when to switch from reading in from the string to expanding? Because it seems like this machine, you could kind of go back and forth
Well,
in a way that you don't actually.
the only time you can expand is if there's a non-terminal at the top of the stack. So you can expand here because there's a non-terminal. The only time you can like munch up strings is if there's a terminal at the top of the stack. So that part is always deterministic. The part that's not deterministic is if you have a non-terminal here, you could expand it in two different ways. Like if A had two different rules for expansion. That's the non-determinism. So yeah, it's kind of trivial. Like, so what are the expansion rules here? So don't read anything in. Turn the S into 0S1. All right, and that's, I guess there's another rule. I could take an S and pop, right? Because it's an epsilon. And then what are the string rules? The string, they're the same. They're always trivial, right? So 1, 1, pop, 0, 0, pop. Okay, so how would you do whoa. What's that? I'm having a lot of fun, yeah. This is fun. You write one machine, you can do all this stuff. Yeah, so how would you parse, how about 0 squared, 1 squared? What happens? So the first thing is you have an S on the stack, and then that gets replaced by 0S1, and then you munch those up, and then S gets replaced by, you munch that up, and then S just gets popped, and then you can get down to the bottom of the stack, and you go to accept. So what happens if you had 0 squared 1 cubed, or say 0 squared 1, and you did this? Why would it reject? Right, when you do this, I guess S becomes, right, I guess so it becomes, yeah, 0S1. It's hard to keep a record of this. What's that?
It happens very fast in the machine.
Yes. So S becomes 0S1, and then you can cross off this 0.
Okay, then S gets expanded.
So now we have
0S11.
Z. And then what happens? That's pretty easy, huh? It's the same thing.
Let's pop the one, we're still there.
Yeah, okay. Am I insulting your intelligence? I hate to do that. No? All right. So yeah, now when we do it, we pop the 0. We can pop the S because there's a rule that says if there's an S, you can always pop it because it's like it can become epsilon. And then, whoops, did I do this wrong? Yeah. now what happens? I can, so I have something like this, 1, 1, Z. I can pop this 1. I'm having a hard time here today. Pop that 1, and then what's, I can't accept, right? I can only accept if the stack is empty. So this won't accept. So that's your push-down automaton. Yeah, boom, and it.
Somebody in class asked me the other day what LR stands for. So I looked it up.
Yeah.
And, I think I said it right when I answered it. But the L part stands for left to right, that you're scanning the input from left to right. Same as the L and LL. And the R part means that it's a rightmost derivation. So this is not an LR machine, so to speak, because you're really doing a leftmost derivation in this. You're always substituting the one that appears at the top of the stack. An LR machine always substitutes the one that would appear on the bottom of the stack rather than the top. And it doesn't,
Yeah.
and it's much harder to come up with a machine from the grammar. It's not as straightforward as this.
For doing an LR. Yeah, LR would be much harder because you have to look at the bottom of the stack, and it's much harder. Here's an interesting thing. I just reminded me of another aside I wanted to talk about, which is what kind of, so now we have a stack. We can actually use a stack to model output. We haven't had output so far in our machines, right? There is something called a finite state transducer, which has output. We didn't talk about that. Well, we did do them when we did like how computers work, right? We had machines that also had output. Right. So you can simulate the output as by using the stack, not using the stack for calculations, but making it be your output. Output display, your TTY or something, right? So what's interesting to think about is what kind of functions you can generate with that output. So I don't know. I mean, I'm just throwing this out so maybe you guys can think about it. So for example, I could take something that, let's say the grammar only has zeros in it, or the language only has zeros. I could come up with a machine that takes a string. Let's say the number of zeros is the number, right? Like so, it represents a number. So if I have 3 zeros, that represents the number 3. If I have 4 zeros, it represents the number 4. So I can come up with I can make a PDA that computes 2 times x. Do you see how I could do that? So I could have a machine that basically, so I don't care about accepting or rejecting now, but I'm modeling computation with a stack. So I could have a PDA, say, that does something like, if I have, so it'll always accept. I don't care about accepting or rejecting. If I see a 0 and there's anything on the stack, I put on 0, 0, anything. Right? That machine will take n number of zeros and give me 2n number of zeros on the stack. All right? So what's interesting to think about is what kind of functions can you generate with a PDA? So I can generate any linear function this way. Right? Could I generate x squared? Could I take a machine that takes in 3 zeros and leaves me with 9 zeros on the stack, for example? Something to think about. So that was just an aside to throw in there. I mean, what do you need for computation? Is this enough? We have a stack. We can get some output. Could we get x squared that way? Is it possible? Anyway, so I just wanted to plant that seed into your brains. And do you guys want to work on some push-down automata? So I guess the options are whoever feels that they need some more work on push-down automata can stay and we'll work on that. Whoever feels that they're fine and dandy with that can go work on their problem set. And if anyone needs help on equal number of zeros and ones, we're here. Or any problem set help.